Okay, so a polynomial graph is a graph that either looks like a line for linear polynomials, a quadratic, which is smiles or frowns, and then a cubic polynomial is your peaks and valleys, right? Or worst case scenario, a wiggle. Okay, those are polynomial graphs. Sinusoidal graphs, by the way, that's how you say this word, sinusoidal. It looks like sinus and then oidal. So sinusoidal, okay? Those graphs look like waves. So it goes up, goes down, goes up, goes down, goes up, goes down. But the difference between that and polynomials is it's the same peak and valley repeated again and again and again. Okay. So we just have to talk a little bit about degree angles and a few bits on, actually a tiny, tiny bit on trigonometry here, just like a smidgy bit. But it's not going to be anything. So if you're like, I don't remember anything about SOHCAHTOA from grade 10, you don't need it. It's just a matter of talking about degrees. So it's about drawing angles from what you did in middle school, actually. We're just going to put some language to it. So this is page 359 in your workbook. Okay. So when we talk about a degree measure, we draw angles like this, right? You've done this forever, right? You've drawn angles. We call the starting point the initial arm, and we call the finishing point the terminal arm. It's just words, okay? So think of this on an XY grid. Your initial arm is always going to be the x-axis. And let's say you draw in 60 degrees. This is what we call the terminal arm. Now this little symbol here, we call that guy theta. Okay, remember that from grade 10. So this is called a rotation angle, right? You've drawn angles in forever. You should know your key points. So this one is 0 degrees. This is 90 degrees. This is 180 degrees. This is 270. And all the way around is 360. Okay. Okay, so just your key markers going around. Good? Okay, so let's just draw a couple angles just to see if you remember how to do this. So if this is your initial arm, if you go up off of it, that is a positive angle. And if you go down off of it, we call that a negative angle. Okay, so a negative angle, so think of it as a positive angle is counterclockwise and a negative angle is clockwise, which seems kind of different, right? Seems backwards. But since most of you don't know how to tell time on an analog clock, it doesn't matter. Just think of positive goes up off the initial arm, negative goes down off the initial arm. That's all you have to remember. So then if you're going negatively, then this becomes negative 90. This is negative 180. This is negative 270, and that one's negative 360 because you're going negatively around through those numbers. Okay. Okay, so when we ask you to sketch, I'm not going to look at Amy's and go, oh, that looks more like 58 degrees, not 60, right? Like we're looking for, did you land in the right quadrant? That's all we're kind of looking for. So 290 degrees is positive. So you're going to start on the x-axis and you're going to go up off of the terminal arm. So you're going to go this way around. So 290, so we would go all the way here to 270 and then a little bit more. So that is 290 degrees. So this thing right here is what we refer to as the terminal arm. And it says, what quadrant did you land in? Well, we landed in quadrant 4. Okay. So negative 135 So again, think of this as negative 90. This is negative 180. So negative 135 means I'm going to start by going down off of that initial arm. So I'm going to go negative 90. I'm going to stop about halfway. So that's my negative 135. Okay? Because I'm going to land somewhere between negative 90 and negative 180. I don't care if you draw your line right smack in the middle or closer to one versus the other. It actually makes zero effect to me. But we landed in quadrant 3. Okay, 750. So again, it's positive. So we're going to go up off of the initial arm. So once around is 360, right? So once around is 360. Twice around is 720. Then I need to go another 30 degrees to get to 750. Okay. So I don't know if you guys have ever heard the expression like when somebody says, man, that guy completely turned his life around. He did a complete 360. You ever heard that expression? Okay. Please don't use that expression in your life because you're an idiot. If you do a complete 360, what have you done? You've turned in a circle, but you're still facing the same direction. You haven't turned your life around. You've just got yourself dizzy. If you want to say someone's turned their life around, say they've done a 180 with their life, not a 360. 360s just make you dizzy. Okay? So when you see that expression, or again, understand that one full rotation is the 360. So I could make this 1750, like 1750. You would just keep going until knocking off 360 multiples at a time. Even though you've gotten nowhere, like just going around in a circle, you still have to show that rotation. You have to show it winding like a spring. You have to show the path of that angle going round and round and round. Okay, so flip to the assignment and just do question number 1. So just just do question number 1 for me. I'm going to give you 5 minutes. Just do that, and then we'll come back and we'll show you something new. Okay, so I handed out this page to you. Okay? Okay, so I'm going to introduce a scary word to you. Please don't freak out. It's just units. Okay? So we have the metric system and the imperial system, right? Volume, we could write it as centimeters cubed. We could write volume as liters. We could do it as cubic yards. We could do, what's another volume one? Tons. Okay? We can do volume in all these different units. Meters cubed, decimeters cubed, inches cubed, right? It doesn't matter. They're just all different units for volume. Do you find the volume of every shape using the same formula? Yes. Right? Well, volume length times width times height for a rectangular prism. It doesn't matter what units it is, right? As long as all the units match. So the units don't affect how we calculate volume. It just affects how you write the final answer. Angles. You guys are used to using degrees. You separate a circle into 4 chunks with each one measuring 90 degrees, and all together they create 360 degrees. Well, another measure is called a radian. So if you go on your calculator, and yes, I got my calculator back, yay, okay. On your calculator, if you hit mode, right here, radian degree, okay? So your calculator is actually got both modes on it. So up till now, so when you were in 20-2, 20-1, 10C, we said that when you were in trig, when you were in the trig unit, you always had to set your calculator into degree mode. Okay, that was just a standard. So when you walked in every day for trig, we said, okay, make sure your calculator's in degree mode, otherwise all the answers will be screwed up. Okay, so in this course, you're going to go back and forth between the modes. Okay, so I'm simply going to tell you what a radian is. You are not required to know how to convert from a radian to a degree or a degree to a radian. You don't have to worry about that. Okay? It's just like saying in junior high, you learned that 1/2 is the same as 0.5, which is the same as 50%. You learned that those three things were equivalent. You learned that 2/3 is 0.6 repeating. You learned that those two things are equivalent. Well, here's a couple of equivalencies. 360 degrees is the exact same size as what we say 2 pi radians. Now, if you punch in 2.2 pi on your calculator, that is approximately 6.28. So if you're like going, what the frick, what? It's just a number. It's just a different unit. It's like saying if you told me the answer was 1/3 and Missy beside you said it was 0.6 repeating, you're both getting it right because it's the same number. All I'm saying is 360 degrees is 2 pi. Smile and nod. 180 degrees. Okay, just let's see if you can pattern this. If 360 degrees is 2 pi's, you stay quiet. What is 180 degrees? 1 pi. Or about 3.14. Now I say about 3.14 because you guys should know by now that pi is the ultimate decimal, right? Doesn't stop, doesn't repeat, doesn't terminate. So let's keep going here. What would 90 degrees be? So if 360 is 2, 180 is 1, what would 90 be? Half of a pi. I'm just dividing them by halves. Now, usually we write this like that. We don't put the 1 in. But if you want to write the 1 in, you do you. Now, I am not going to show you how we get those two equivalencies because that is an entire Math 30-1 lesson, and I mean a 90-minute lesson teaching you how those two things are the same. Okay? We're not going to do that. You're just going to smile and nod and go, okay, 360 degrees is 2 pi, 180 degrees is 1 pi. And that's all you need to know. You guys do think visually though, right? You think in terms of size. So just to show you something here. I just said 180 degrees is 1 pi, which is essentially saying 3.14. What 1 radian is about 57 degrees. So most of you should be able to visualize about 60 degrees, right? Because that's 90, that's 0. Right? Typically, if you go like this, like if you just hold your hand and I say, okay, make an angle with your hand, most of you go like that, right? You don't go like that. You don't go try to do an L. You just kind of comfortably go like this. It just so happens that physiologically, if you make your hand at the same angle as your forearm, see how that's the same angle? And then you just hold your thumb parallel to the floor, that is always 60 degrees. So you see how oh, I got a ruler right here. Okay, so you see how my forearm lines up with that? So if I keep my hand the same angle and then I just hold my thumb at parallel to the floor, that angle is 60 degrees, like this angle right here. Okay, so that angle is what we call 1 radian. 3 of those, okay, what's 3 times 60? I won't make you do this in your head. What's 3 times 60? 180. 180 is 360 degrees, right? 60 plus 60 plus 60 is 180. So 180 is about 3 of these chunks. Each chunk is a radian. That's what a chunk is. Okay? Where does that chunk come from? Well, imagine you had imagine you actually had a pie in front of you. Pizza, apple, ice cream, I don't care. But imagine you physically had a pie. And you're going to cut yourself a slice of pie. This is the crust. These are your cuts. Okay. If you make the crust the same length as the cuts, so it's the perfect cut to crust ratio, right? You get the same amount of crust as you do cut. That angle that you make here will always be 57.3 degrees. Always. And it doesn't matter if you're talking about a 14-inch pizza or a personal pan. It doesn't matter. If you keep the crust the same length as your two cuts, the angle that it makes will be about 60 degrees. That's what a radian is, folks. Okay? So because a radian can be standardized, most mathematics uses radians. That's why the default on your calculator is in radian mode, not degree, because radians allow us to be way more precise. So for example, when I draw this as 60 degrees, could it be 59.7? Could it be 60.2? Could it be 60.0003? Could be any of those. But if I express that angle as a radian, like this, I can write it out exactly what it is. No roundings necessary. That's the difference between 30-1 and 30-2. 30-1, they have to do all the conversions into these exact radian numbers, whereas you guys are just going to be like, that's a radian, and you're done. Okay? So we are going to be graphing. These are called sinusoidal functions. We're going to be graphing on an XY grid. That X grid in degrees is going to go from 0 to 360. So in radians, it's going to go from 0 to 2 pi because these are equivalent. Now, the reason why you're going to see the radian is that when we use the calculator, so remember I said how we're going to do regression, right? We're going to do list 1, list 2 regression. The answer on your calculator will always be in radians because that is the default mode that it is set to. So if you're like going, hey, Schnorr, can I just set it to degrees, then have it find the answer in degrees? No. As soon as you try to do a regression, it will automatically change the mode back to radians. You cannot override that feature. So you have to know how to solve it in radians. So I'm just introducing to you what a radian is. 2 pi is 360 degrees, which means 1 pi is 180 degrees. I have some kiddos in 30-1. So they, in 30-1, they see trig for 6 weeks straight. Like it doesn't stop. Trigonometry makes up over half the diploma exam in 30-1. So by the end of trig in 30-1, those kids stop thinking about degrees and only think in radians. But for the first week or so, most kids will scratch out the 0, 1 pi, 2 pi, and write in 0, 180, and 360 because it's what makes sense to them. Okay? You guys unfortunately don't have the digestion time, so you just need to know those 3 markers and just understand that it's just different units. It's like saying 0.51 is the same as saying 0, 1/2, 1. It's the same thing, it's just different units. Okay? Okay, we're going to skip this. We're going to come back to this when Melissa's here because I need Melissa here for this. And I want you to go to page 369. So I did hand it out to you. I think it's just because this is prettier than what the picture is in your workbook, but it is matching page 369. So there's 2 words I want to talk to you about is period and amplitude. Okay. So what we're going to do in this unit is we're going to look at the graphs of these waves. Okay, so they're going to be these waves that appear on the graph. So all of our graphs are going to look something like this. They're going to be these waves that just go on and on and on forever. Okay, so the period in fancy speak, it's the length of one interval of the function, or in other words, it's the length of one repeating pattern. Okay, so a period, the period of a graph is how long it takes for one pattern to repeat. So if you just go down here, so let's take a look at this little pattern here. Where am I at? Okay, let's do it like this. Whoops. Okay, so if I start at 0, 0, so the pattern goes up, down, up. And then do you see? It repeats again. Up, down, up. So the period is the length of one pattern. So how long is one pattern? 8. Now I don't know if it's 8 seconds or 8 degrees or 8 radians. I don't care. I'm just going to say the pattern is 8 units long. It's the length from start to finish. Now another way you could look at it and say, okay, this graph goes from 0 to 16. And from 0 to 16, I have 2 full cycles. Well, what's 16 divided by 2? 8. Okay? So usually when I'm looking for my pattern, I usually start on the y-axis because then I'm always starting at 0. So if I start here, I'm going to go up, and then I'm going to come back down. And then the pattern repeats itself. It's going to go up, and it's going to come back down. So how long is it from there to there? What's the period? 6. Now, there's some of you little geniuses in here. There's always one every year that say, okay, I don't see the pattern like that, Schnorr. My eyes go from here to here. I see this as my pattern, and I'm going to repeat that over and over and over again. No worries. Where are you starting at? 3. Where are you finishing at? 9. So what's the period? 6. So it doesn't matter what part of the pattern you isolate. You just have to make sure you isolate the entire pattern. So I saw the pattern as bottom to bottom, 0 to 6. Somebody might see the pattern as peak to peak. That would go from 3 to 9. The period is still 6, regardless of what part you're looking at. Okay, so that's period. Yep. Is your hand up? Okay. So the other one I want to talk to you about is amplitude. Amplitude is half the height. So if this is the top and this is the bottom, this is what we call the height. So half that height is the amplitude. We're going to wrap it up here after this. So how far is it from 10 to negative 10? How much distance does that cover? 20, right? So the amplitude is half of that. So the amplitude is 10. So what's the total height for this? It goes from 6 to negative 2. So what's the total distance here? 8. So the amplitude will be 4. Okay? So that's it. We'll stop there. So what we're going to do tomorrow, so keep these 2 pieces of paper. What we're going to do tomorrow is we're just going to backtrack and we're going to look at the graphs of the sine curve and the cos curve. We'll do that tomorrow, and we'll just use our calculator to help us with that. And then we'll start, just like in polynomials where we had to talk about the constant term, the turning points, the x-intercepts, the end behavior. We had all those terminologies to cover. We have similar terminology to cover with this, but I'll tell you right now, the 2 most important words that we're going to cover are period and amplitude. So we've already done 2 of the 3 words, and so yeah, we're well on our way.